Eskom coal-fired power stations. These giant power stations are familiar landmarks on the Mpumalanga Highveld and in Limpopo. 13 operational power plants make up nearly 85% of Eskom's generating capacity. 2 new power stations are currently under construction. Towering over 110 meters above the foundations, one can clearly see the 6 boiler houses that shape the horizon. Within these weatherproof enclosures are the boilers themselves. Boilers are highly complex machines that convert the chemical energy contained in the coal to kinetic energy in the steam. This steam is then piped to the turbo generators, where this energy is transformed to electrical energy or electricity as we know it. Boilers are manufactured entirely of steel tubes that are welded together. Over 650 kilometers of tubing is used in a modern boiler. The evaporator tubes are arranged to form a gas-tight container or furnace enclosure. This is where the combustion of the coal takes place. Within this furnace, the tubes of the economizer, superheaters and reheaters are arranged to absorb the maximum amount of heat from the combustion process. Our boilers are more than 90% effective in achieving this transformation of energy. Boilers are constructed from the top down on site. Therefore, they cannot be replaced. Modular replacements are also not possible, because if heat exchangers have to be replaced, they have to be cut out, tube for tube, and reassembled inside the boiler. It follows that they have to be maintained to continue to function effectively to the end of the station's life. Process description. 2 different processes take place in a boiler. Firstly, the combustion process, where the energy in the coal is converted to heat. This is achieved by grinding the coal to a fine powder, heating air, and then using fans to blow this hot air and coal powder into the furnace. This coal ignites to form an intense flame that can reach temperatures of up to 1,600 degrees Celsius. The coal burnt in our power stations is of the worst quality in the world and contains up to 48% ash. Ash is the common name for the incombustible mineral matter contained in the coal. These minerals take no part in the combustion process, but cause extensive wear to the mills and tubes as they are highly abrasive. Our coals are also slower to burn than Northern Hemisphere coals. For this reason, our boilers have to be built much taller to allow more time for the coal to burn out. The second process is heat transfer. This is where the heat from the burning coal is absorbed by water to generate steam. Boiler designers ensure that the maximum heat is absorbed by the steam from the hot gases passing over them. One way they achieve this is by spacing the tube elements close together. Currently, less than 10% of heat is wasted in this process. The heat transfer process starts where demineralized water is pumped into the economizer. Water is preheated by waste heat from the furnace. Next, it flows upward through the evaporator. Radiant heat from the combusting coal is absorbed here, and about halfway up this wall, the water turns into steam. Steam is then piped to the first stage superheater directly above the furnace. More heat gets absorbed here. Steam then gets fed through to the second stage superheater. Both these superheaters consist of hundreds of tubes running from the front to the back of the boiler in a serpentine manner. This high-pressure steam is then piped to the third stage superheater, where it is heated to the design temperature of 564 degrees Celsius. The steam is finally piped to the high-pressure turbine, where some of the work is done to drive the generator. The cooler, lower-pressure steam is then returned to the boiler, where the reheaters again heat it up to 572 degrees Celsius and is again piped all the way back to the intermediate and low-pressure turbines, where the rest of the work is done to drive the generator. What can go wrong? As with any pressurized system containing potentially dangerous substances, any leak or failure in such a system is regarded as a risk. The severity of the failure will guide the actions to be taken to deal with it. In boilers, the failure itself presents as a tube that bursts or cracks, and high-pressure, high-temperature water or steam escapes. In Eskom, 70% of tube failures result in a forced outage. Boiler tube failures are the leading single cause of unavailability in generation and in the rest of the world. The contribution of boiler tube failures to the system unavailability has been as high as 50% in a month, but the average has decreased steadily from 30% in 2008 and is currently hovering around 20%. In the last financial year, 159 tube failures occurred on the 79 boilers in service. Boiler tube failures are classified in terms of their failure mechanisms. When analyzing the boiler tube failure statistics over the past 8 years, it can be seen that there are 6 failure mechanisms that dominate, and therefore are the primary focus of the boiler tube failure reduction program. Fly ash erosion, welding defects, and overheating failure mechanisms will be discussed. Fly ash erosion. Fly ash erosion failures can be caused by one or a combination of the following: poor or deteriorating coal quality or an increase in ash content, high peak velocities within the boiler caused by design deficiencies, poor workmanship relating to tube alignment and the maintenance of flow correction screens, inadequate testing and inspection plan or inadequate engineering assessment of the plant condition. These failures usually occur in the economizer and the first stage reheater, or between the tube bends and the water walls. The failure has a fishmouth appearance and consequential damage is usually extensive due to the mass of water or the steam that escapes and which damages adjacent tubing. Welding or repair defects. Welding defects are introduced during the welding process, and over time these defects will emerge as tube failures. The majority of welding defects are introduced during the construction of the boiler, where only small samples of the construction welds are tested for defects. Until about 6 years ago, maintenance welds were also not fully inspected. There are a number of reasons why welding defects can occur, and as this list is extensive, only a few are mentioned. The skill of the welder, the control of welding consumables and equipment, poor supervision, dirty, windy or cramped welding environment. These failures can occur anywhere in the boiler where a weld is located. Thus, there are tens of thousands of potential failure locations in each boiler. These failures usually result in a small crack or pinhole. If these failures are detected soon, and if their consequences can be evaluated, the boiler could continue steaming for some time before having to shut it down. However, the majority of the leaks cause adjacent tubes to rupture, and an urgent shutdown is required. Long and short-term overheating. Long-term overheating failures occur because the tube has reached the end of its life. This happens after 200,000 to 300,000 operating hours. The material becomes brittle and can no longer contain the steam pressure. It is important to establish whether the failure was premature or not. An engineering and metallurgical investigation is required to establish the root cause of premature failure. Short-term overheating failures, on the other hand, occur because the tube has quickly reached a temperature high enough to soften the tube and it bursts. The most probable causes of these failures are exposure to temperatures higher than design over a long period, or exposure to sudden overheating due to a flow blockage, tube starvation, or excessive firing. Long-term overheating failures usually occur in the third stage superheater due to it having the hottest tubes in the boiler. The failure usually has a thick-edged fishmouth appearance, a crack, or it can be a clean break. The consequential damage is usually extensive, not only from steam washing, but because of mechanical damage caused when these ruptured tubes swing about inside the boiler and breaking other tubes as they whip around. Short-term overheating failures can occur anywhere in the boiler, but are most prevalent in the water walls, the final stage superheaters, or final reheater. Tube leak detection. Early detection of a boiler tube failure is essential to minimize the extent of consequential damage. If this is achieved, the offline time required to repair the failure is largely reduced. A power station is a noisy place, and it is impossible to hear a tube leak unless you are standing right next to an open boiler manhole. To overcome this problem, all the Eskom boilers have been equipped with tube leak detection equipment. This system consists of microphones fitted at openings around the boiler at various levels that are connected to a processor that listens specifically for the hissing sounds of a boiler tube leak. The information for each microphone is processed continuously and is presented to the operator in the form of a bar chart on a separate display in the control room. Normal conditions are indicated by green columns. An alarm is received when one of the microphones picks up a higher noise level, and this is displayed on the screen as an orange column. An audible alarm is also sounded to draw the operator's attention to the problem. Operators have been trained to respond to this alarm by carrying out a series of cross-checks with other instrumentation to see if there are any other signs of a leak. An operator is also sent to the boiler to look and listen for any telltale signs. If a boiler tube leak is confirmed, a decision to shut the unit down is given by the responsible person on site following discussion with system operations and the divisional executive generation. How do we repair boiler tube failures? Unplanned outages have a negative effect on the national grid, and detailed procedures have been compiled to ensure that each phase of the repair is carried out. The shutdown and forced cooling. Once operating personnel have to shut down the boiler in accordance with safe operating practices, the boiler is then force cooled with the forced draft fans at a safe rate. During cooling, engineers and maintenance staff carry out planning to ensure that when the boiler is opened, repairs take place safely and in the shortest possible time. Once cool enough, gas tests are conducted to ensure that there are no dangerous gases present inside the boiler. If clear, a permit is issued to allow persons to enter. It can be seen that the only way to enter a boiler is through manholes the size of car wheels. All equipment, spare tubing and personnel have to pass through the small opening. If the location of the tube leak is not safely accessible, a scaffolding team will immediately start building platforms inside the boiler to ensure safe access to the inspection team. A small team will then enter the boiler to find the tube leak and carry out an investigation to determine the failure mechanism and most probable root cause. Inspectors also carry out ultrasonic tube thickness measurements to identify those tubes that have been eroded by steam or water and which also have to be replaced. The repair. With the scope of work finalized, the maintenance team will commence repairs. In some cases, the failure location is not accessible and perfectly good tubes have to be cut out to gain access to the damaged area. Once the damage has been repaired, the tubes that were removed have to be welded back into place. The quality of the repairs is of utmost importance. Each weld is X-rayed, and the X-rays have to be signed off by a competent person. If the X-rays reveal defects in the welds, the tube is cut out and re-welded, and the quality checks have to be repeated. Tube samples of the failed tubes are sent to our metallurgical laboratories to confirm the failure mechanism. The inspection authority, acting on behalf of the factory's inspector, has to apply his stamp of approval of all work carried out on the boiler. Operating personnel then commence preparing the boiler and the rest of the unit to return to service. Returning the unit to service. They remove all the isolations, carry out complete plant inspections according to checklists, and provide management with the assurance that the unit is safe to return to service. Once the final approval has been given, the boiler has to be filled with water, the air supply established, and oil burners put into service to heat the boiler up to a point where it is safe to allow coal firing. Once steam is produced, the turbine can be started up. The average offline time to repair a boiler tube failure in Eskom is currently 63 hours. What is being done to reduce boiler tube failures? Eskom has one of the most comprehensive boiler tube failure reduction and cycle chemistry improvement programs in the world. A basic program was established in 1994, which yielded excellent results. This program was reintroduced and further enhanced on request of Mr. Damas in May 2008 and was compiled by a team of Eskom's boiler, metallurgical, and chemistry specialists who are recognized for their knowledge and expertise. The program is based on the Electric Power Research Institute's boiler reliability and cycle chemistry improvement models that are applied successfully all over the world and has been further refined with inputs from companies such as Structural Integrity Associates and the RWE. Engineering also determines and verifies inspection and non-destructive testing techniques that will detect damaged tubing so that systematic replacements can be planned into the available outages. Since 2008, a dedicated multidisciplinary team of Eskom specialists have been working with the power stations to ensure that the program is implemented according to the directive and that a common approach is applied throughout. The team also stays abreast with international developments and proactively addresses potential failure mechanisms. Statistics show that the team is continually making progress to reduce the number of failures and increase boiler availability. There are, however, a number of challenges that are slowing progress, and these are: inadequate planned outages of sufficient duration to carry out testing and inspections to determine deterioration rates, find damaged tubing, and to execute the required replacements or repairs. The availability of skilled engineers on site to determine the root cause of the failures and develop testing techniques. The poor condition of some of the boilers. Overcoming these challenges will make it possible to achieve our targeted performance and support Eskom in becoming one of the top 5 performing power utilities in the world.